Frequency response gives us an output in terms of an input. So in other words, if I hit an input, if I hit a system or a structure with a certain input, the response that I get from that input, reference with respect to the input, is my frequency response. Now that's a simple in layman's terms that I can put that. We went through the mathematics last time, and it really only was a bare minimum I could give you to talk about it intelligently. We could spend an entire semester looking at the details of that. And of course, if you're going to write the code for dynamic signal analyzer, you have to dive into a lot deeper, right? You don't really have to do that, but I want you to at least understand where it's coming from. So what is a frequency response? Some of you take controls and have different controls. We studied it in there pretty good earlier in the semester in here. We did look at what we called steady state response through the harmonic input, and we did get something that looked basically essentially the same thing as a frequency response magnitude phase. In fact, the first exam had a question that asked the magnitude of the system. That was basically the magnitude phase of the response. How much up here do you think we're giving it? We use it all the time, and the controls, most likely you're doing the model or the time domain model different models and directing those in terms of transfer functions. But at some point we talked about trying to measure these things. How many measurements are we done with? That's response. And frequency domain measurements are always done. Okay. And so same information is usually embedded in there. However, when you have a lot of different things going on, which we do in structures with more than one modes, frequency response is definitely frequency matching is the way to go. We're down, by the way. All right, so in any event, the main takeaway is frequency response is a complex quantity of complex quantity of functional frequency. So we will generally look at the magnitude of it and give unit frequency, whatever your output is, your input. So, or if we've got acceleration as our response to our output and our input force, then the units are going to be, for example, acceleration divided by force per unit. Okay? Magnitude is exactly that. It tells us how much at the frequency we get. All right? That because it's a complex quantity, that's not the whole picture, though. To get the whole picture, we can look at what? The complex quantity. If I say, hey, I'm going to give you a complex number. What do you need for the number? And you say 4. Real imaginary parts. Right? Parts. And that's all it really meant by complex number, because it's multiple different things complex. But the point is that there's just 2 quantities. That's it. And if you think of that, the magnitude phase, in my mind, that's why you deal with that. And so that's generally what I will do. You see clearly, try to scratch what you. All right, you have to look at things, you have to look at. All right, so what does this tell us? You data like this. What does it tell you? Well, this tells us that our frequency response, actually our frequency response, has some peaks. If you count that little guy there, really 3 main peaks in the range of 0 to 1,000 hertz. That means it's pretty system. Over that range, yeah, pretty good model. 3 modes pretty much that's what's going on up to 1,000. All right, and what this shows here is coherence. And last time I mentioned that there's 2 ways to calculate the response. So we actually analyze them. Whenever we do signal processing on data, we calculate them both ways and we look at the ratio. 2:1. It's not 1. What that tells us, the ratio of coherence is not 1. It's less than 1. And what that tells us is that at that frequency, the coherence is not 1. That not all of the response, not all of the here it says you have a frequency F1, and all of the response is at that frequency is due to the input. So if we're measuring acceleration of structure, we do a hammerhead, all vibration, all acceleration. If it's zero, we don't have any cases of zero, you're pretty close to 0 on 0. And that in the value here. In that case, then none of the response. All right? Now, the only area that really matters for our purposes, you're going to see here, we're to really extract the modal information and the vibration model information. We're really only interested in where this really responds. Those are the good points of interest for us, not really points, but ranges. So we see we're able to get a peak from, like, say, 500, 600, 500, or 450 to 550, and then like 8 to 9, 950 to 1,000. Those are the ranges of frequencies that are really we're going to be extracting data. So those areas are important. All right, at least 0.9 better. All right, you certainly need that requirement. If you don't have that, then you need to figure out what's going on in your test, because some other input is affecting your response, and you need to get that out. You need to somehow remove it by doing your test. All right, so here's just an example of magnitude of frequency response, and we're going to use this to extract frequency. Okay, and that's the frequency response. So over a given frequency range, we look at where the system peaks, or the magnitude peaks, we can identify those as natural frequencies of the system. Right? And really, to some extent, it doesn't matter where you're measuring or where you're implementing on structure, where you're exciting the structure. The only time it becomes a problem is, remember when we talked about nodal points and nodal lines? In that case, the system doesn't respond and says, no, you have to put, in location, you have to put an accelerometer to measure response. You put it on a nodal line or nodal point, and you strike. It's not going to measure that. It's not going to measure that mode. So what would happen? Let's say we put an accelerometer on a node to the second node. This little piece would show up. That would show up. You understand that? Why? Because the structure is not really vibrating there. No. Or similarly, if we were striking or exciting the structure at a nodal point or nodal line. Does that make sense to you guys? You're not exciting. You're not really exciting that mode. You can't excite that mode because it's not vibrating. All right. So I'm going to show you a video a little bit here that shows nodal lines very clearly on the place, on our main place. And so we'll come back to that. But that's an important point. So as long as you have reasonable separation between peaks, you use just the magnitude to extract magnitude to extract frequency of the peak. Bandwidth, which helps you estimate the bandwidth. And you can also use the peak value, the magnitude of those frequencies to extract motor information. We get everything we need. And all of those data, all of everything we need for mobile or mobile model. Now we need more than one measurement to get different locations of motion, but we don't. We only need one location for measurement. So first of all, wherever it peaks, we can extract the next frequencies. You got 3 peaks, which make up the next frequencies. You guys have heard the term bandwidth. All right, so when you've got a narrow band like this, which it's not so narrow, the bandwidth is defined as what? It's a frequency range, but what defines the range is what we call the half power points. This comes from it doesn't matter where it comes from. It's what we call wherever you have like a mode of peak. This goes down vibrations, of course, as well in different controls or other dynamic areas. You come down to what are called the half power points. What the heck is that?
simple terms, we're actually going to point if we say, if we had a magnitude in decibels, if we had an dB at scale, dB at any, not just sound, but vibration, resonance, we have a lot of scale. You come down to 3 dB. So this peak up here, now this, the magnitude of this guy is 10 dB, the bandwidth would be defined where the magnitude is 7 dB. We have functions, take 10, subtract 3, that defines the bandwidth. 20, doesn't have power. All right, so that's a logarithmic. Now, we're not going to use logarithmic in here. Controls do. Control use lots like that. If you're like, so you have a control system. For linear units, not decibel or logarithmic units, they have power point defined as the magnitude times 0.707. All right? So in this case, it's 10 in linear units, not dB. Then we would multiply that by 0.707. So a bandwidth would be defined by the range of the magnitude is greater than 0.707. All right, similarly to this one. So just for one magnitude frequency response plot, we can extract natural frequencies and we can extract the damping ratio. So what kind of information could we get from this? I gave the magnitude scale. 3 natural frequencies, omega 1, omega 2, omega 3, and 3 damping ratios, beta 1, beta 2, beta 3. Those would be the damping ratios for each mode. 3 modes. So there's a lot of information from one magnitude plot we can extract. Number of modes over the frequency range, the actual frequencies, and the damping ratios. So here's an example where we just have one peak. So one mode in this frequency range. And I'm going to show you, I don't remember if this is on the station or not. So the damping ratio estimate is the bandwidth, which is the frequency difference. Usually in linear units. Control units would be just like I said, code class, power that but the damping ratio of the peak is given by the bandwidth divided by 2 times the center frequency. So in this case, the peak frequency is, say, 10. Back over here. So let's take a look at this. We've got magnitude versus frequency. This point right here is what? The frequency of this peak point is 9.6. So that's our natural frequency. That's also what I call the center frequency. Okay? Peak frequency or center. The peak value at that frequency is what? Looking over here, we're between 2 and 3. I've got written here 2.55. So our peak value is 2.55. To determine our bandwidth, we take that 2.55 and we multiply it by 27. Divided by square root of 2. Multiplied by 27. All right? Yes. The right test question. What? That's the right test question. What? On the that one. I mean, I'll show you that slide. All right. So when we take 2.55 and multiply by 0.707, what do we get? 1.8. All right. So we draw a horizontal line at 1.8. What does that define? This right here. Bandwidth. All right. That's the bandwidth of this peak. All right. And so we drop vertical lines, and you can use whatever symbols you want. I use subscripts A and B because we're already using 1, 2, and 3, right? The numbers. So I use A and B usually to indicate bandwidth. So the bandwidth is going to be 11.4 minus 7.2. So we see that. So 11.46 minus 7.27. So that information is given here
apply. All right, so plugging in our bandwidth, which is the difference in the frequencies here. Plugging in our bandwidth, dividing by 2 times the center frequency gives us an estimate of the damping ratio for this. All right, does everybody see the sharper that peak gets, the smaller our bandwidth becomes? What happens to our damping ratio? It also gets smaller. That makes sense. Right, the broader it is, the given center frequency, the larger the damping ratio. All right, so that was a simple example. Here's one that's a little bit more involved. Estimate the natural frequencies and damping ratio. More of that. It's helpful. Everybody heard it, right? Previous slide, and I'll just continue with this slide to make a good example question. Of course, it is. It was. My handwriting. So in this case, we've got problem is estimate the natural frequencies, damping ratio from the following frequency response data. Got a data is this? Well, this is the magnitude versus frequency of frequency response measurement. And so we see, what do we have? Over the frequency range shown, 55 to 90 radians per second, we have 2 peaks. All right? So we have our first natural frequency is approximately 59. That draw, go ahead and draw. I'll give you a problem like this, a homework or a test question. Go ahead and get your ruler out or whatever drawing tool you have, draw a vertical line, and then just write 59 so you can see where things came from. That way, if you write a number that's wrong, let's say you just, I don't know, something goes on in your head and snaps the wrong way, and you decide that this is 69 or 49, okay? It's not, it's 59. But if you draw a vertical line here, press the wrong number here, we're like, well, you at least do what you're doing, you just somehow mistake, wrote the wrong number. Anyway, 59 for that, let's look over here, this is between 80 and 85. I estimate that that's roughly 83. Well, she could write 82.5, probably close enough. And then what do? We determine the peak. So this first one, the peak value is about 8. So the bandwidth is determined by taking 8, multiplying 0.7 by 0.707, we get 5.7. I draw a horizontal line at that magnitude, that defines my bandwidth. All right, so my bandwidth is basically this frequency difference, which is 64 minus 56. All right, so zeta 1 is going to be the bandwidth for this peak, 64 minus 56 divided by 2 times the peak frequency, the center frequency. All right, everybody see that? Any questions? Similarly over here, the peak value here is about 5.8. We see that? Multiplied by 0.707, we get 4.1. Draw a horizontal line. This line right here defines my bandwidth. All right, so 76 to 86, my bandwidth is 10. And now we can estimate zeta 2, our second damping ratio, to be the bandwidth divided by 2 times the center frequency. All right, any questions? All right, so just from one frequency response measurement, assuming the input, we're not exciting the structure, we're not measuring the responsive structure at a location where there's no point or no line, we should be able to get the natural frequencies and damping ratios one there. All right, what about mode shapes? Well, mode shapes are a little bit more involved. And so there are a couple different things that we can do. One of the things we could do is we could just put our structure on a shaker and drive it over a range of frequencies. As soon as we start getting a response, like seeing an actual vibration, we hit it with a strobe light. There's enough displacement, we might be able to see what's really happening that way. We could use the Trelonding approach, which is basically you've got a flat structure. You can sprinkle like sand on it and then drive it over a range of frequencies. All right? Whenever you hit a natural frequency, the scan will, number one, you'll see it, the vibration, but number two, the scan will collect wherever there's a notable line. All right, so everybody's got the course. Where? Yeah. So this is a little bit different than that. There's no fluid out here. So, all right. You can also use a strobe light. We used a different wine glass. But let me show you the drum head. The drum head's actually kind of an interesting one.
It's the lowest frequency vibration pattern, circular membrane. This circular membrane is a dense rubber band.
Okay, so it looks like it's going about 1 cycle a second, something like that. It's slow. Why do you think that is? Yeah, something like that. That's the actual frequency is generated in the background. 2.2. That's actually the driving signal. The function generator is going to the power area. It's been driving this audience underneath this. All right. And so you've got that mark. And then there's a strobe light flashing on, so that all you're seeing in this recording is you're just seeing whenever the light flashes. So like you're not seeing it. So what's making it look like it's making it look like it's moving a lot slower. So that's the power of the strobe light. Remember you use strobe lights in here? All right, here's what I know that. So one of the interesting things you can do with like fans. I'm gonna learn from my kids in the little we did, before strobe light fan. If you adjust it, you can make the fan look slower, stop, the other direction. I mean, it's very interesting. But basically, it's a very useful tool to actually see the shape. All right. So we've also drawn some circles and lines on here. The reason we've done it is because there's going to be different mode shapes. Right now, you see the first mode, the whole thing moving up, and then the whole thing moving down. But then it's going to start doing things like this. The little line will be a line here, and then you'll also have ones where some of the circles are going down, some of the circles are going up, so you'll have another line that's actually a circle. Keep an eye on that number on the signal generator in the background because that's the actual frequency this is moving at. You wouldn't be able to see it without the strobe light on.
This lowest pattern, the entire membrane goes up and down together as one piece. The thing goes together. Here's the second pattern. The same membrane, goes at a little bit higher frequency. Half of the membrane goes up, the other half is putting down, and there's a line right across the diameter of the node that doesn't vibrate at all. Here's the third pattern. Membrane, there are two sections, actually it's kind of like a cloverleaf pattern. Two opposite sides of the membrane move up together and the adjacent sections move down. There's four regions that move alternating up and down. Here's the fourth pattern. The center of the membrane moves opposite the outside edge. There's a circle that doesn't move at all. It's kind of the center and the outside edge move in opposite directions.
All right. So we can use empirical methods. Is what background music? That's a good idea. More dynamic. Empirical methods like Slavi's method, use it, or like this sort of like very useful time, but structure has very large. We also have more formal methods which are based on All right, first thing I want to show you here is a Gelati's approach. Of course, he was doing this before we had audio speakers, like a magnetic shaker, things like that. So what he would do is he would basically take different structures, give an example of square plate, attached to a stand in the center of the plate. And then what he does is take a violin bow and hold it along the edge of the plate. We play colors of bow. All right. So why is the bow like so many different things? No? Good. Any questions? Yeah, Christian. Yeah. Anything else happening there? Yeah. Actually, most bows are made out of horsehair, right? So horsehair, if you look at actually your own hair under a microscope, it's not really smooth. It actually has a jagged, I don't want to say like a knife edge, but kind of like that. So if you pull that across something, you're excited and broad range of things. So even if you're playing the lowest note or the highest note on violin or whatever instrument you're playing, you can excite the broad range. And it's basically pulling, releasing, and the rosin adds enough friction so you get to stick to it. It doesn't just grab it. All right, so he does that, and he can excite certain modes, but by placing his finger, you see his finger from his other hand, by putting his finger at different positions along the edge, he's forcing the note, a nodal line. Violinists do it, guitar players do it, we force notes when we play harmonics. Right? You put your finger close to where there's a note, it forces that note to dominate. You get the same thing. You basically sprinkle sand on there, do this, and collect it as a nodal line. And there's books, or a book, with hundreds of pictures of different modes of plates of different geometries. Nowadays, when we do the demonstration, we use a small shaker, electromagnetic shaker with a plate on it. Same thing here, and we drive it with this is a small signal generator with enough current to drive a small shaker, so a little bit of power angle in there. I just want to show this to you. It's going to go through a broad range of frequencies, and we're going to get it to 1,000 hertz range, which use or not, but our ears are most sensitive around 1,000 hertz. All right? It may be loud enough that it'll become irritating. So another little lesson for you. Not only can we have modes on structures, we have acoustic modes in volumes. All right? Now, because of the carpeting and because of the sealing material, it'll absorb some of it, but we'll still probably push the volume. There will be enough energy to create acoustic modes. At 1,000 hertz, the wavelength of a mode is about a foot. All right. So if you're sitting there and you're in excruciating pain because the frequency is hitting your ear, because you happen to be rated an antenna rather than a node, you can plug your ears or you just move your head a little bit. All right. For lower frequencies, the wavelengths are bigger. So, for example, 500 hertz, the wavelengths would be more like this. So, if you happen to have your ear right at one of the anti-notes, you're going to actually pick up more sound pressure level than you would. So, if it gets irritating, of course, feel free to plug your ears or just experiment and move your head a little bit. All right, so I don't want to waste any time talking about this. But a mode, so with a mode on the structure, you've got relative displacement, right? A large displacement, at a nodal line or point, you have no displacement. So what else is going on? Acoustic modes, acoustics, we're sending out sound pressure waves, right? So the sound pressure level, which would be equivalent to the motion level or displacement level of the structure, is what's varying. So the nodal points in an acoustic mode are low values or zero values of sound pressure. All right. If you got your head where your ears were really loud, that you're not anywhere near a node. You're in between where sound pressure level is varying the most. Turn it on. I won't touch the volume. When you've had enough torture, just raise your hand and I'll shut it off. Varying the frequency on the signal generator that's driving the shaker. When it gets close to the natural frequency, the sand collects along the nodal lines. That's the first nodal line. That means that the plate's moving at that frequency everywhere except for the sand collects. Everywhere it's black there, it's moving up and down at that frequency. You get to a point where you should be a little irritated. I turn it up. All right, your hand. That hand go up and up. All right, so that is an example. Now you may say, hey, how many times do you have a structure that's flat? I had a student, grad student, silicon wafer, solar cells. We are interested in looking at the vibration spectrum, including both shapes and angle ratios, as a function of the residual stress, possible defects in those components. And if you didn't want to actually put sensors on it, we're trying to do everything now in content. Microphones to measure frequency response rather than accelerometer, and then we use philology, very small amount of very fine grain how to really validate our final. Yes. That's probably over 1,000 hertz. Yeah, we can put the pitch.
We did that year this year. And I think the highest we went to be about 700. Right.
That's it. Yeah. No, I didn't turn the volume up. Yeah. So our ears are both sensitive. You ever looked at the frequency response of your ear? Anybody? So of course, everybody says we can hear between 20 and 20,000 hertz, right? Depending on whatever. But it peaks, and it's not a sharp peak, but it's gradual. It peaks right now. This is 1,000 hertz. That's where our ears are both sensitive. And then it kind of falls in both directions. All right. By the time we get anywhere, near 20 hertz, 20,000 hertz, it drops quite a bit. All right. I would call it, but yeah, it's why we call it an entry frequency. It can't be, so I would really call it. It tends to fall off. Usually, and it has to do with dynamics here. Honestly, physiology here, I haven't studied other than to know that it's not. Like, so when you use a sound level meter, anybody use a sound level meter before? The mics on a good sound level meter are flat. It's flat. So you have to turn on what's called A weighting, and it makes the mic respond like. Right. So if you're making noise and code enforcement comes, your neighborhood, they're standing with some of the schools going down. Another county. They will come if you're making excessive noise, whether you're a company, an industry, or a resident, certain times of the day, they'll come with complaints, they'll take a measurement, but they'll use it a weight because they want to mimic what you're out of my. All right, so what I want to do is I'm going to show you the formal modal test approach. But first, what I want to show you, I just want to show you the data and just get you to appreciate that you don't really even need a whole lot of mathematics, just a little bit of common sense to really understand how to use start motion. Okay? So here's an example. I jumped ahead to 306. Here's an example of a structure. It's fixed on the left. So the structure is actually structure. Fixed on the left edge. 3 over here, here else. And I've got 3 different locations marked out, 1, 2, and 3. All right? Now, what I'm going to do in this test, I've got an accelerometer shown in the figure at point 1, and I've got a hammer hitting at point 1. All right? And then I've got it says FFT. These used to be called FFT analyzers. Nowadays they're called dynamic signal analyzers. We got a dynamic signal analyzer over here. We're measuring the analog signal from the accelerometer. We're measuring the analog signal from the impact hammer. So we've got an input and a response. All right? We can take a frequency response measurement between the response at this point and the hammer at this point, hammer input at this point. All right? As long as that accelerometer or hammer, let's say point 1 doesn't correspond to a node of one of the modes we want to look at, then we should be able to measure all of the modes we want to look at. All right? So let's just look at that data. I'm gonna purposely try to make this a little bigger. Obviously. All right. So that is. I'm trying to ignore this right here is the magnitude. This is the magnitude of the frequency response measurement. So we have our hammer hitting at point 1, location 1, and our accelerometer at point 1. What we see is over the frequency range and the frequency range. Over the frequency range, here to here, we've got 3 peaks. We've got 3 active frequencies. All right, we can extract those. Draw a vertical line to extract those. Also, the little top, go in and you look at the peak values of each one of those, multiply by 0.707, and get the bandwidth for each peak, and estimate zeta 1, zeta 2, zeta 3. Just from this magnitude right here, we can get the 3 active frequencies and the 3 active ratios. Right? How many of you feel confident you can do that? It's a little trickier because this scale and this is a little tougher. But I feel confident that you can do it. Like you suggested is a problem, this would be tougher than the scale. But you can do it, right? What if we took, you can think back to that figure that I just showed you, what if we grabbed the accelerometer and moved it to 2, to location or point 2, and still hit the hammer at point 1? Just don't worry about math, don't worry about anything. What do you think is going to change? The magnitude of what? Yeah, the magnitude. Do you think we'll get the same frequencies? How many people get the same frequencies? Yeah, you're right. You're right. So you hit the line glass here, you hit the line glass here, you're going to get the same, it should be the same natural frequency. Naturally what it wants to vibrate at. However, because of mode shape, we know that even at a given mode, at different locations or positions, the magnitude is going to be different. All right, so if we move, I'm going to give it a new name. When we move the accelerometer from point 1 to point 2, our magnitude instead of being H11 is going to be H21, right? So we grab the hammer location. There's a response. What do we get? We
We still get a magnitude for the frequency response. All we did is move the accelerometer. We still get the same three natural frequencies. It may not look like it, but you should get exactly, you should get within estimate area. You should get the same damping ratios. They should be the same. But, like you said, the magnitude is going to change. Why? Because the motion, right? You expect, even at the same mode, right? This is the mode. And my arm's that plate. Let's say that's the mode. If I put an accelerometer here, at that mode, at that frequency, the magnitude is smaller here than it is here, right? That's all it is. All right, so we can use this. Yes. We could have derived it, but I didn't. We could have derived it. So basically what it does is, there's another thing that we could have derived that I did. So we looked at vibration models, multi-vibration models. We're pretty much left them in terms of mass, damping, stiffness matrix. We decoupled them and we wrote them in terms of natural frequencies, damping ratios. But one of the things, there's another form of those equations we could have written. So instead of mass, damping, stiffness, we could have written them in terms of mode change. And define the frequency response or the extension of the frequency response from mode change. We didn't go down that path. We could have, but I didn't. I haven't for years in the undergraduate class. But we could have. And part of that is, once you get to your frequency response equations from your models, if you set your driving frequency, your natural frequency, everything simplifies significantly if you get two useful equations. The first one is the estimate equation for zeta, which is an estimate because you're still taking it from data. And then the other one is the one I haven't showed you yet, which we're going to use to extract. My point is, you don't even really need that to appreciate what this data provides. Yes.
So, but this is pretty much the same as why it's doing this subject. It really doesn't really matter where you get it from, because to find the natural frequency.
Well, as long as you're not exciting your vector measuring your response at one of the lower lines, you should be able to get the most. Okay. All right. Now, if you want it, so if you get natural frequency and damping ratios, it doesn't really matter where you're at. That's a good point. However, if you want to get mode shapes, you've got to move. Let's just take it now. You've got to move the accelerometer. You've got to move back to your response. Or better yet, if you had three accelerometers to begin with, in one hammer, you could get all your data measured in one set. You wouldn't have to move and measure the response to three locations.
That would be for where you would say that where the person can be hit with a hammer. I don't know if here.
You can hit it, doesn't matter. You can hit it somewhere else. No, it's going to respond the same. It's going to respond the same.
Based on where, so that would just give you the mode for where you place the accelerometer.
The modes are going to be the same. So the structure is going to respond. The structure wants to actually. Let's go back to the single degree freedom system. You get a single degree freedom system, with any sort of input, like a transient input, it's going to respond at the natural frequency and the damping level that it actually wants to be based on that. Multi-degree freedom system similarly has natural frequencies, damping ratios, and mode shapes that are inherent to the mass damping characteristics. Doesn't matter where you hit it. In fact, if you hit it with a hammer, you hit it with a shaker, you can hit it with a shaker with a random input, a harmonic, sometimes input, whatever, you can get the same information. All right? All right, so what do you think is going to happen if we continue to hit at location 1, but move these around to location 3? What do you think is going to happen? You're right. If you said you'll get the same 3 peaks, you're right. You should estimate the same damping ratios and the same frequencies, but you can see the magnitude has changed. All right, so let's take a look at this for a minute. I'll get you guys to write it down so I don't have to go over and write stuff down. But let's just take a look at the first mode.
This would be the first mode. Why? Because it's the lowest frequency, right? Ignore the data over here for a minute. We'll get to that. Let's look at this right here. At this first frequency, the magnitude here is what? 0.2, 0.1, 0.2, 0.3, say 0.35. Close enough for what we're trying to do. Let's write that down. The magnitude here at the same frequency is about 0.9. All right. And then the magnitude here is about 2.5. Everybody with me? So 0.3, 0.9, and 2.5. All right? Those are the three values for those three different locations. So that frequency, it kind of suggests that this is what's happening, right? 0.3, this is going up and down 0.3. This is going up and down 1 or 0.9, whatever. This is going up and down 2.5. Right? How many think that's true? All right. One potential little problem is, how do we know they're in phase? We have to look at phase. All right. We have to look at phase, make sure they're phase. Chances are they probably are, but we want to make sure. All right. So the frequency response, remember we told you the frequency response function and frequency response function, complex quantity that has magnitude and phase. Magnitude gives the magnitude of the mode shape, the phase gives us the sign around. All right, so let's take a look at the phase at that frequency. So you see this vertical dashed line at that first frequency? You just expect the 3 peaks. This is the corresponding phase of the same three frequency response measure. We're going to draw a vertical line at that first frequency. We're going to look at the phase. Minus 90, minus 90, minus 90. They're in phase. All three of those measurements, 0.3, 0.9, and 2.5, they're all moving in phase. So if you wanted to write a mode shape for that first mode, it would be those three numbers. What were they again?
0.3,
0.3, 0.9, 2.5. So if you wrote those as all positive to the 3-by-1 vector, that would be a reasonable estimate for the first mode shape. What if you put a negative sign in front of all of them? You'd be correct. They're all still in phase. All right? Good? Yes? What if they're not what? Then let's look at that example. So, what do you want to do? We can do all 3 months, or do the second and third one. Which do you want to do? Do the third one? Do the third one? We'll do an example. So we'll either do, that was the first natural frequency in the first mode. As we look at the second or the third. Which one do you want to look at? Third, all right. The third frequency, again, you can extract the peaks. Let's come over here so I can look at it straight on. These are just estimates for me looking at it. This is 0.1, this is 0.2, so the magnitude here is about, let's just say 0.15. No, it's not right, but it's close enough, 0.15. This looks like it's the same, maybe a little bit lower. Let's say 0.13. And then here, this is like 0.8. All right? So we say 0.15, 0.13, and 0.8. All right, those are my 3 values. We look at the phase for that mode. We draw a vertical line at that frequency. We got minus 90, plus 90, minus 90. All right? So in this case, pick whatever you wanted to call plus 90 phase a positive sign, that's fine. Negative 90 degrees phase, minus 9, that's fine. But just be consistent. But what we're going to have is we're going to have 0.15, let's say negative 0.15 with the negative phase. Then this has got a positive phase, so we'll call this one plus 0.13. This last has got a negative phase, minus phase, so this will be minus negative 0.8. What's the mode shape for this third one? 3-by-1 vector, a negative 0.15, positive 0.13, and a negative 0.8. Everybody see that? And you can normalize it how you want, but for right now, it at least least gives you an idea. Now, I can't even do that with my hand because this and this are going up and down together, this is going out there. All right? Do the same thing for the second one. How many people think you do that? Good exam question? I ask it all the time. No? All right. Now we can formalize this whole approach. We can formalize this whole approach, and that's what we've done here. If we go through, if we were to take your multi-degree unit system model, the mass spring damage system, go beyond that 8-step mobile analysis, rewrite those in terms of both change and frequencies and damage ratios, determine the frequency response of those, which is basically writing in the frequency domain. It's a little bit involved. And then evaluating only where the frequency is equal to natural frequency, it reduces to this. So I don't think I've done this in this class, maybe I have, but this is literally, it can be shown. I'm not showing it to you. I can. In fact, it just derived it the other day in my grad. Like hours. It's probably in your book, the idea is we have a frequency response between every possible input and output. And if you take control, you have to take control. This is not going to hurt you learn this. If you have a system, it doesn't have to be a structure, but if you have a system that has 2 inputs and 2 outputs, you have every possible combination of an input and output or input and response will give you a transfer function or frequency response. All right? So 2 inputs, 2 outputs gives you how many transfer functions you need to define the system. 4, 2 inputs, 1 output. 2, 3 inputs, 4 outputs. 12. Very good. That's it. So in this case, we're hitting in 1 location. That's our input. We're measuring at 3 locations. We've got 1 input, 3 outputs. The way we've set it up, instead of how we like here with this. In this case, we have 3 frequency response functions. 3 frequency response functions. All right, and so we're defining the terms of the input and the output, and then as I said, if you take our multi-degree system equations of motion, which we use a step procedure model analysis procedure, right there in the frequency domain, we can get this relationship when we evaluate at the exam. What this is it basically gives us a relationship between magnitudes of our motion and the magnitudes that we can extract from a frequency response measurement, and then also damping ratio and frequency. So on the right side of the equation, this is stuff we can extract from our frequency response measurement. The left side of the equation is what we need to determine the magnitude of our mode shapes from the measurements. All right, I didn't derive this equation, this is given. If you did not test, I'll give you. All right, so first of all, what is, if ui is the ith vector, let's say it's for 3-degree system, we get 3 by 1 vector. Then a 3 by 1 vector times a 1 by 3 vector, which would be the transpose of that, is going to give you what? The outer product is going to give you a 3 by 3 matrix, right? Not the way we want it to go. But not this time, all right? So if you take, if this is a 3 by 1 vector, its transpose will be a 1 by 3. So this product, it's called an outer product, will give you a 3 by 3 matrix. Okay? What this is describing here, defining, is a 3 by 3 matrix. It's SR element. So there's just one element of that 3 by 3 defined by the location of the accelerometer and the location of the input of the handle. Right, so S and R define just one element of that matrix. So there's 9 elements. This is just one of those elements And not only are we just looking at one element, we're just looking at the magnitude. So we don't know if it's positive or negative. We just know it's magnitude with this equation. All right? And you have to look at the phase to determine if it's positive or negative. All right, so what I want to do next is, so here is an example of that matrix. Here's a 3x1 vector U, 1. Here is the outer product, so 1 times 1 transpose gives us what? You get to this multiplication, right?
Yes,
A1 times A1
you can do that.
This, A1 times this, A1 times etc. We get 9 elements. However, if you look closely at this, if I give you the first 3 elements here, the first row, or if I give you the first column, or if I give you the diagonal, you can determine what? The rest of them. You don't need 9 different measurements. You only need 3 to determine everything you need. All right? So that's an important point which we're going to use. I just wanted to make that point. And here it is in words. Even though this has, I'm trying to test for elements only need n of them. Only n of them. Only n frequency response measurements are needed. So in our case, 3 are needed, not 9. All right, so here we are back to this, which is where we were about 20 minutes ago. Here's that data. I'll pull down a little bit so we can see it all. Here's this data. So we've got 3 frequency response measurements, magnitude and phase. One at the top is that we have the hammer hitting at location 1 and the accelerometer measuring at location 1. 2 plots in the middle are magnitude and phase. When we move the response, the accelerometer location 2 still striking the hammer at location 1. And then the bottom frequency response, magnitude and phase, how much quantity when we move the accelerometer to location 3. We've already used this data to determine an estimate of the mode change, right? What I'm going to do is I'm going to use this equation right here, which is a little bit more formal, to extract the same information. All right? So first thing we're going to do is I've got on the next slide all of this data summarized. So what information do you need here? If I give you this data, what do you need? That'd be a good question right there. What do you need? I don't even ask you to do it. Just what do you need? Well, what I like to start is I'll just tell you the order that I like to do it. First of all, I'm going to see 3 peaks, so I want those 3 peaks. All right? So column -1, -2, -3. These 3 peaks. This looks like that's the case. These are our 3 frequencies. That's the first thing I did. All right? Then just make sure that they're the same. There's no issue. Then draw vertical lines with those frequencies in my magnitude plots, and I draw vertical lines with my phase plots. All right? The phase plot, if we have proportional damping in normal modes, the phase should be at plus or minus 90 degrees, or 5 degrees. Might not be exact, but it should be close. We're going to model it. All right. Then the second thing is what? Then I want to go to the quick one. I'll probably pick the nice top one here. This and this one because I did not bandwidth like it. So I'm going to use probably this and this one to extract my damping measure. Data 1, data 2, data 3. Right? Using either one. I probably use this one. This stuff here. Pick the peak value, like you said. The rest of you were thinking, I'm sure. Multiply that by 0.707. Draw my bandwidth. Bring my bandwidth. The damping ratio data 1. Bandwidth. That peak divided by 2 times 7. Do that for the other 2. And I got my estimate for entry frequencies. And then I want to make 2, make 3. And now I've got my estimate for damping ratios. Data 1, data 2, data 3. I can show all my work. Got the data. And then what do we need for mode changes? Magnitude. You need to know the peak here, you've got here, so 9 magnitudes, and then you need to know the phases. Give it plus or minus 90 degrees for each one of those. That's 9 pieces of data and 9 pieces of data. I'm telling you this because here's a question for starters. What do you need to do this from this curve? List it. That'd be a good question. I think it would be. But my thoughts on good questions for you guys are not going that well. Yes. Then your phases wouldn't be plus or minus 90 degrees. Good question. Now, you could extract, but it would be much more involved problem. All right. Yes. Good question. Oh, go ahead. Yes.
Just to clarify, we need the 3 frequencies, 3 magnitudes, and 3 phases. We do it. Like check the
Graph. Yeah. So for this particular case, right, you want peak values. So first of all, let's just write down natural frequencies. So -1, -2, -3. And you can get those from really any one of these. The damping ratio is going to be 3 of those. You get any one of these magnitude blocks. Okay, natural frequency damping ratio, -1, -2, -3, -1, -2, -3. Then what? Then you need the magnitudes at your natural frequency. So that's just 3 here, 3 here, 3 here. The magnitude at your natural frequency, all 3 magnitude blocks. Then you need your phase at your natural frequency from all 3 phase blocks. There's 9 magnitudes and 9 phases. Okay? Honestly, if I were in your shoes, if I was 100% clear, I would ask the same question. Good question. All right. Now I've done that because this data is a little tough to read. I zoomed in on it. I think it's in your book. I zoomed in on it and pulled this data for all 3 modes. Here's the data. I showed you how much data and you get 0.01. Here's my magnitudes. Here's my phase. At those frequencies, at the natural frequency. Actually, this is just the first mode. So let me go back. So we're going to look at just the first mode shape. What information do we need for just the first mode shape? I was talking about what do we need total to get everything. Next slide, we're just looking at the first mode. What on here pertains to just the first mode?
Well, it's the first
This
one.
vertical line, everything associated with this vertical line, which includes the frequency 10. The damping ratio, zeta 1, which we can determine from the bandwidth either here, or here, right? What else do we need to get the mode shape? Magnitude only at that frequency, right? And then the phase only at that frequency. So that's what's on the next slide. So the first mode shape header should be the giveaway, right? So there's my frequency, there's the damping ratio, there's the information. So the first we talked about 4. Phase, all 3 phase blocks. I'll give this question and I'll say, students will be, let's say, I got minus 90 for all 3 of them. They'll show me that they've got a red dot here, here, and here. That's wrong. Right? Why? This is the second natural frequency. This is the third natural frequency. Nothing to do with the first one. Nothing. All right, so that's the information that we need. Everything that we need is given here. In fact, sometimes we get to do that. I want to give plots like L, the information, and then this generic equation
I for subscriptions, I and J instead of numbers. But in this case, you plug in what we have for the first mode. So we have the magnitude, the first magnitude plot, at omega 1, magnitude, the second frequency response of the first frequency, and the magnitude of the first frequency response of the first frequency. Multiply those magnitudes by 2 to 1 omega 1 squared. And that gives us the magnitude of these elements of U1, outer product of U1. All right? Again, this equation would be given, not with the subscripts there, but I and J. All right? So this is what we now have. Using this raw data, we now are able to calculate the magnitude of the outer product for 3 elements of this outer product matrix. So now what we're going to do is we're going to define U1 as having elements A1, A2, and A3, calculate the outer product in terms of those, and then going back to the previous slide, you see, hey, this here, which is element 1, 1, has to have a magnitude of 0.8 is equal to A1 squared, therefore A1 is what? Square root of that, 0.9. Phase is minus 90 degrees, so I'm going to call that a negative number. That's going to be negative 0.9. Similarly, this from the previous slide, T1 is 1.8. You define it as this doesn't matter. A1 times A2, we already know A1 times A2. And then the third thing, the last quantity that was calculated on the previous slide was this element, and this element, 3,1, which is A3, A1. We know A1, so we can calculate A3. Phase is minus 90 on all of them, so all 3 of these are negative. That's my motion. What did we do before we get it out of this now? All right. Is it proportional within the range? As you pull those numbers off the plot, we would use the actual numbers that I use proportional. Gets you at least close to reality. Is this going to be a little bit better? Yes. But the other approach doesn't involve any math. It gives you an idea what that is. Any questions at all? All right, we can do the same thing for the second mode. If I said extract the information you need for the second mode, what would you give me? First of all, what 2 vertical lines are important? Just stuff at the second frequency.
Yeah.
The second mode, wherever you see a peak, second peak, first peak, second peak, everything is this frequency, this vertical line right here. The most important, if I get that for example, is to draw a vertical line at that second mode there, and then at that same frequency, draw a vertical line, and then write something down here that says everything I need for this is obtainable along these 2 vertical lines, right? Give a chunk of value in your problem like that is understanding. So we can extract all that information. What about the third mode? If I wanted to study the third mode, then we look at the third attribute. Everything in this third line, third vertical line, here and here. That's the information that we need. So if we look here, I basically, I don't know why I put all of this on one slide, but I did. Here it is. All the information for the second mode, information for the third mode, and then following using that same equation, different subscript. The second mode, we're going to say second mode. The third mode, we're going to say third mode. Yes.
What is the difference of the two columns in that matrix?
I mean, they're all related. The only significance is that to determine these elements, A1, A2, A3, you can literally use any column, the first row and the first column, use any row column.
Basically a system.
Yeah. There is some significance. We talked about moving the accelerometer, not the hammer. We could let the accelerometer alone.
All right, just to leave you with this, we take a simpler problem. Basically, we just have 2 points, with 2 frequency response measurements, with 2 magnitudes, 2 phases, 2 frequencies, 2 mode changes. If I give you set of data, instead of giving you plots of data, but extracted data, this is that information you need for the first mode. This is the information you need for the second mode. I can give you a problem like this. Instead of giving you data that you have to extract stuff from, say here, given this data that's already been extracted from your frequency response measurements, determine the mode shapes. So in this case, your mode shapes are going to be 2x1s, but the procedure is the same as before. The outer product, U1 times U1 transpose, is going to be a 2x2. You only need the information for the first row, first column to determine the output of U1. But it's the same procedure we followed on the previous example, and I'll leave you with that. Magnitude and phase information is given, and so we can calculate the magnitude and phase of motion. All right, good point for us to break. How many of you are not going to be here next class? A lot of folks. So the point of the plan is to do a motor test out, and then talk about your first 5. So we'll still proceed with that. And the problem was I didn't change on Thursday. The project wanted to do a week from Thursday. All right?